This is the fourth topics in the course of probability and stochastic processes, in which we are going to talk about random variables and the distribution on these random variables. A random variable R on a probability space S is a total function whose domain is the sample space of the probability space. Therefore, we make no restriction on the codomain of the total function. Given a probability space S and PR, then a random variable on this probability space is any total function R whose domain is equal to S. That's it. That's the only restriction that we have. As long as it is a total function and the domain is a sample space, then it is a random variable on the probability space. Now, the codomain of this random variable can be any set, but it is usually a subset of the real numbers. Well, it may be discrete, for example, just a couple of numbers, or it can be continuous, it can be large, it can be small, and so forth, but is usually a subset of the real numbers. Now, the name random variable is not actually precise because it is not a variable like we see before, but a function. This is a function that maps every outcome inside of S to a number. Suppose we toss three mutually independent and unbiased coins. Mutually independent means that the tossing of one coin does not influence and is not influenced by the tossing of the others. Unbiased means the probability that the tossing produce head and tail is equal, namely 1/2. Now, let C be the number of heads produced on a tossing. Yeah, so it may be 1 if there is only one coin that produce head, 2 if there are 2, and 3 if there are 3 coins that produced head. And then let M equal to 1 if the tossing produces 3 heads or 3 tails simultaneously, and M is equal to 0 otherwise. Now, every outcome of this 3-coin tossing experiment uniquely determine the values of C and M, and the outcome of this 3-coin tossing experiment is actually shown here as. So there are 8 possible outcomes starting from HHH. It means that the first coin produces head, the second also produces head, and third produces head, and so forth. And we see for every outcome that we have here, this outcome will uniquely determine the value of C or the value of M. Hence, C and M can be regarded as functions that map the outcomes from S to numbers. More specifically, C is a function that maps every outcome to a number with the following rules. CHHH is equal to 3, for example. CTHT is equal to 1. Well, because what? Because the only thing that we have to do is to count the number of H inside of the outcome. Map M, on the other hand, is a function that maps every outcome to a number with the following rules. MHHH is equal to 1, and mttt is also equal to, so these are the only ones, and the rest is equal to 0. Therefore, C and M are random variables. So furthermore, we can actually see that C is a function from the sample space to a set that contains 0, 1, 2, or 3, while M is a function from S to a set that contains 0 and 1. Indicator random variables. An indicator random variable is a random variable that maps every outcome to either 0 or 1. Such random variables are also called Bernoulli variables. The variable m that we have seen in our previous example is an indicator random variable. So basically, an indicator random variable is nothing more than any random variable R that map S to this particular set 0 and 1. Now, indicator random variables are closely related to event because both partition the sample space to two blocks. In the case of indicator random variable, the two blocks are the block containing outcomes mapped to 1 and the block containing outcomes that map to 0. So for example, if this is the sample space, then we can partition this. An indicator random variable will partition it into two blocks that whose outcome are mapped to 0 and to 1. Similarly also with an event is nothing more also than something that partition the sample space, namely partition it into the outcomes that are the element of the event, for example this one, and the other one will be the complement of that event. Hence, for each event E, we can associate an indicator random variable IE such that IE omega is equal to 0 if omega is not an element of E and is equal to 1 if omega is an element of E. Therefore, there is a direct correspondence, a one-to-one correspondence between an event and an indicator random variable. Furthermore, events are also closely related to random variables. A random variable that produces n different values partition the sample space also to n blocks. Yeah, so for example, if we have this as a sample space, and if we remember again the random variable c that we have seen before, there are 4 possible values. Then this random variable c must partition S to 4 blocks. We can consider this as block 0, block 1, block 2, and block 3. So there are 4 possible values, then the sample space will be partitioned to n blocks. For example, the first block, namely when c is equal to 0, contains TTT. The second block here contains 3 outcomes and so forth. Now each block is a subset of S and therefore it is an event. Now moreover, we can view an equality or an inequality involving a random variable as an event. So this is basically an event. So C is equal to 0. We can consider this as an event when the random variable has f value 0. But more than that, we can even say that C less or equal to 2, for example, is an event. So C is equal to 2 is an event containing outcomes THH, HTH, then HHT. And even C is less or equal to 1 is also an event containing outcomes TTT, TTH, THT, and HTT. Because these are events, we can talk about the probability of those events, the probability that are determined by the random variables. For instance, the probability of C is equal to 2 is equal to the sum of the probability of those events. Yeah, there are three of those outcomes. There are 3 outcomes inside, so we have 3, 8. Now, the probability of C less or equal to 1 is equal to the sum of all the probability of the corresponding outcomes inside of that, namely these 4 outcomes. So this is 4 multiplied by 1/8 is equal to 1/2. So that means that random variables are actually just another way of describing an event. But this way of describing an event, it gives our flexibility. So we can basically manipulate it. We can change the values. We can put it into more a quantitative way of describing events. And that way we can vary it later on. And we will see the strength of this way of describing events. One of the strengths is that we can right now talk about the function of random variables. Previously, we will not be able to represent, to think about a function of events. But right now, we can talk about functions of random variables. Random variables can be combined to form a more complex random variables. For example, suppose we toss 2 independent and unbiased dice. Let di be a random variable representing the outcome of the ith die. So that means that di is a function. Di is a function from the sample space to a number from 1, 2, 3, and so forth until 6. What is the sample space? Well, the sample space can be considered as the pip. For example, this one. The pip on the die. Yeah? These are the sample space, for instance. Now, we can talk about the probability. For example, the probability that D1 is equal to 3. So we toss one die D1 and it produces 3 is equal to the probability that D2 is equal to 3 is equal to 1/6. We can form a more complex random variable T, for instance, which is equal to D1 plus D2. This is a function right now. So T is a function of 2 random variables, which represent the sum of the 2 dice. Now, if we think about this, then T is also a function with a particular sample space, and we map this into a value. What are the possible value? The possible value or the possible sum of the 2 dice, namely from 2, 3, 4, and so forth until the last one, the largest one, is 12. What about this sample space? This sample space can be formed. For example, the first sample space will be this one. So where each die produce 1 pip. The second one maybe this one. The third one, maybe this one, and so forth. So you can imagine that. Now we can compute the probability that t is equal to 3 is equal to 118, because there are actually two possibilities there. Yeah. And then the probability that t is equal to 7 is equal to 1/6. Conditional probability. Combining the conditional probability with events involving random variables does not create any problem. For instance, we can talk about the probability that C is larger or equal to 2 if M is equal to 0. This is the probability that at least two coins produce head if not all coins produce the same result. M is equal to 0 means that not all coins produce the same result. We can calculate this. So this probability C is larger or equal to 2 if M is equal to 0, according to the conditional probability, is equal to the probability that C is larger or equal to 2 and M is equal to 0. So intersection M is equal to 0 divided by the probability that M is equal to 0. What do we have? When do we have this intersection? Namely, this happens when we have this outcome THH, HTH, then NHHT. So you see, in this case, we have C is larger or equal to 2. There are only two of them. But when M is equal to 0, so that means that we cannot have HHH in that case, because this is actually okay with this part, and C is larger or equal to 2, but is not an element of SM is equal to 0. Divided by the probability that M is equal to 0. This is 3/8 divided by 6/8, which is equal to 1/2. So the conditional probability proceeds similarly with the previous one. Just treat these random variables as events. What about independence? The concept of independence also applies to random variables similar to events. Two random variables R1 and R2 are called independent even only if for all x1 element of codomain of R1 and for all x2 an element of codomain of R2, either the probability that R2 is equal to x2 is equal to 0, or the probability that R1 is equal to x1 if R2 is equal to x2 is equal to the probability of R1 is equal to x1. So this is basically the analogy of analogous to the first definition of independent. This maintains that the probability of R1 is equal to x1, namely this event is not influenced by the occurrence of R2 is equal to x2. It remains the same. Now, as an alternative formulation for this in a similar way is given by the following definition. Two random variables R1 and R2 are called independent even only if for all x1 element of codomain of R1 and for all x2 element of codomain of R2. Look at this. The probability that R1 is equal to x1 intersection R2 is equal to x2 is given by the product of those probabilities. The probability of R1 is equal to x1 multiplied by the probability of R2 is equal to X2. So you see, we have the similar fashion. But right now, the conditions that we have to check is based on the possible values of those two random variables. Let's take an example. For instance, an interesting question is, are C and M independent? C and M that we have seen before are not independent if we can find two. So if you can find a pair of values x1 and x2, yeah, such that the probability that C is equal to x1 intersection M is equal to x2 is not equal to the probability of C is equal to x1 multiplied by the probability of M is equal to x2. And actually, we can find such values, namely when x1 is equal to 2 and x2 is equal to 1. Think about it. X1 is equal to 2 means that, yeah, x1, this one is equal to 2 means there are two heads occurring produced by the produced by the tossing. So there are two heads produced by the tossing, while M is equal to 1 means the tossing produces H, H, H. Yeah, so this must produce H, H, H. And of course, their intersection will be an empty set. Yeah, the intersection, so there will be an empty set. So in that case, the probability that C is equal to 2 and M is equal to 1 will be equal to 0. But on the other hand, the probability that C is equal to 2 multiplied by the probability of M is equal to 1 is given by 3/8 multiplied by 1/4, 3/32, 3 divided by 32. Because they are not the same, then we can conclude that these two random variables C and M are not independent. One example, one counterexample is enough for us. What if we have more than two random variables? In a similar fashion, we can also extend this definition. We can generalize this definition. Like events, the concept of independence also applies to more than two random variables. Random variables R1, R2 up to Rn are mutually independent even only if the probability that R1 is equal to x1 and R2 is equal to x2 and so forth until Rn is equal to xn is the same as the probability of R1. So it's equal to the probability of R1 is equal to x1 multiplied by the probability of R2 is equal to x2 and so forth until the probability of Rn is equal to xn. But you have to check them for all possible x1, x2, x3 and xn. So, yeah, how many conditions do we have to check? Well, the number of conditions that we have to check is equal to, yeah, is equal to this, the product of the cardinality of all codomain of those random variables. So if you see, for example, this is basically the product of I is equal to 1, I is equal to 1 until n, yeah. So the codomain of Ri, and you take, and this set, and these conditions, the number of the conditions may be large, yeah. So if we have a large number of values, possible values in each of these random variables, then this can be really, really large. In the next part, we are going to talk about distributions on those random variables. Distributions basically an intuitive way to say how those random variables, how the values of those random variables are distributed, what are their probabilities, and so forth. There are two ways to define the distribution of the random variables. The first one is called the probability density function. Let R be a random variable with codomain phi. So let's return to this one. So assume that we have a random variable R. Of course, the domain of this is still S, but the codomain, we call this V. Yeah, a codomain V. Then the probability density function of R is a function that maps every element of phi to a value between 0 and 1. And this is defined by this formula, the PDFR of X. So X is an element, X is an element of the range of R, is equal to the probability that R is equal to X if X is an element of the range of R, and this is equal to 0 if X is not an element of the range of R. So this is simple. The PDF basically tells us the probability when the random variable has a particular value for all possible values. Consequently, if we add them all together for the possible value, if you take the possible value of this random variable and add their PDF, it must be equal to 1. Namely, the sum of the PDF Rx for all x inside of the range of R must be equal to 1. This is an example. Suppose we toss two independent and unbiased dice. Let T be the random variable representing the sum of the result of the two dice. Then the codomain of T is equal to phi, namely a set that contains 2, 3, 4, and so forth until 12. And also the range of this random variable, the range of T will also be equal to V. Now, this is the graph. This graph here basically tells us about the PDF of random variable T. Take for example, when we take x, namely a value inside of phi equal to 6. So when x is equal to 6, this is the probability. This basically tells us, yeah. So this one tells us that the probability that random variable T has value 6, namely 536. And this is exactly the PDF of T at value 6. So this means that the PDF is simply gives us the value of the probability when a particular random variable has a particular value that is taken from each range. So that is why we call this distribution, because this function tells us about how the value of those random variables are distributed, are given probabilities. The second way of defining distribution is by the so-called the cumulative distribution function, CDF. The cumulative distribution function CDF of R is a function that maps every element of phi to also to a value between 0 and 1. And this is defined by the CDF R of x is equal to the probability of R is less or equal to X. So the only difference is this one, the probability that R is equal, less or equal to X. So from the definitions of PDF and CDF, then the CDF R of X is equal to the probability that R has value less or equal to X. Then this is equal to the sum of all the probability of R is equal to Y for all Y less or equal to X. And this is equal to the sum of the PDF R of Y for those Y less or equal to X. So the CDF is just the sum of several values of PDF. The PDF Rx is the probability that R is equal to X, while the CDF R of X is the probability that random variable R has value less or equal to X. Several random variables may have the same PDF and CDF, and this PDF and CDF represent the distribution. They are actually just the same way of expressing the distribution. Different way, but they means the same. We can transform a PDF to CDF and vice versa. Continuing with the previous example, the CDF for the random variable t is given by this one. This is the CDF t of x. Yeah. So for example, when I take x is equal to 6 here, x is equal to 6, for example, here. So this revert to the probability that those random variable has value less or equal to 6. So this simply means the sum of all values y less or equal to 6, the PDF t of y. Yeah? So we just sum all of the PDF from 0 until 6. Now usually the CDF is also commonly denoted by function f, capital F. This is the CDF, yeah, while the PDF is usually denoted by small f, ft. This is the end of the fourth topic of the course of probability and stochastic processes. Thank you.